by you telling me what you think it means when I say that two figures are similar. How would you explain that? How would you maybe give an example of that? What would similarity mean when we're talking about, let's say, just limit it to geometric shapes? Okay, go ahead, Jack Kramer. Oh, to scale something. We've talked about what scale means, scale models, scale drawings. What does it mean to be a scale factor, to have a scale? I like that. Go ahead, Jack. The same, but what's different about it? Okay, so mostly the same, but some difference, some subtle differences possibly. Go ahead. Same shape, different sizes. Okay, good. Issa? Same angles, you said? Difference, the sides are different, though? I like that. Anything else? Well, you guys know what it means to be similar. You use the word similar all the time. Okay, this is similar to that, or whatever. Similar doesn't mean exactly alike, right? Because if it were exactly alike, you'd say that they're exactly alike. So similarity, there's obviously some differences. Now, what I'm hearing throughout here largely is that the sizes can differ, but the shape remains the same. So do you think a triangle could be similar to a rectangle? I asked that question in other countries. You'd be like, yeah, one's red and the other one's red. They're similar, right? Not geometrically, no. Triangles can't be similar to rectangles, okay? They have to be the same polygon, for instance, in this case, to be worked. But yeah, I like what we're saying about have to be the same shape, different sizes. So we're going to learn some new terminology here today. Here's the formal definition of similar figures, which you guys just kind of nailed in discussing that. And I'm going to put a symbol at the end of it, just a single squiggly line. What is the name of that symbol? Does anybody? What is it, Ben? What is it? Well, approximately it would be two of those. Yeah, yeah. I'm just thinking there's a name for that symbol. Do you know it, Jay? What is it? Tilde? Yeah, this isn't Spanish, but yeah, it is. I know what you're saying. I was asking you because I legitimately couldn't remember what it was called. Yeah. Ava, do you know? What's that? Yeah, that's what I was wondering. Like, what is it? What is it called? In math, for our sake, it means similar. It means like one object is similar to the other. I'm going to call this similarity. All right. So we learned one new symbol today. We're going to talk about some others here. If you look at this diagram that you have on your paper, I think yours is labeled exactly like mine. You have two triangles, clearly two triangles, but they have a lot going on with these triangles. Inside the angles, they have some markings that I need you all to be familiar with. Obviously, you're familiar with that, okay? Right? The right angle symbol. But what does it mean? Like, this has a single arc in it. This has a double arc. And I've got a single arc here and a double arc here. Does anyone have any idea what the arcings imply? What does it mean? And if you don't, that's okay. I didn't expect you to. So if you don't, just pay attention and we'll figure these out. Arul, what do you think? Yeah. Yeah. So you're saying like this angle Y that has the single arc and B would have the same measure, right? And then you're thinking Z and C. He's right. Okay. They refer to angle sizes. Now, it's not like, oh, it has a single arc. That means it's 60 degrees. Or if it's double arc, it has to be 120. No, it doesn't tell you about the actual number. It's telling you how does it relate to another angle. And Y is congruent or has the same measure as angle B. Okay? Z is congruent or has the same measure as angle C. I don't even know what those angles are. Okay? Doesn't matter to me. I just know that they're the same. Okay? Which actually I brought up the word congruent. So down at the very bottom, you have two definitions. Let's scroll down there. Congruent. Did you guys know what congruent meant before? I just said the word. I didn't realize. I was wondering if any of you weren't sure what that meant. Typically, we use the word congruent when we refer to angles. So angles that have the same measure, same size, same measure. And then the other thing we're going to talk about here are corresponding parts. And these are basically just parts that match up. They line up with each other on different shapes. So when I tell you that two figures are similar, or it doesn't have to be two figures, you have multiple similar figures, but if I have figures that are similar, there are two things that have to be true to prove that they're similar. And I want to see if you guys can develop these two criteria that we're going to use here. Can just take a minute, maybe just quickly just discuss with each other. Can you come up? If I can get one from one group and one from another group, then I'm good. Or if I can get two from every group, that'd be awesome. But what two things do you think have to be true to prove that figures are similar? Remember, similar just means same shape, different size. Okay, so what would make two shapes look the same, but just be different sizes? Okay, it might seem like a very simple question. But, all right, so just see if you can come up with an idea. I don't think. Talk it over. Can anybody give me one? One thing that has to be true, do you think has to be true? Nadia. Okay, so yes, has to be proportional. Now, how do we measure proportional, Nadia? Like, what are we looking at when we measure proportional? Same scale? I like that. Okay, so we're looking at the lengths of the sides, right? I like that. One of the things that have to be true, we would say that the corresponding sides are proportional, all right? Corresponding sides are in proportion. What's the other thing that has to be true? Okay? The angles have to be, and I'm going to use a different word for proportional. Congruent, yeah. Because the shapes could be, like one could be much, much larger than the other, but the corresponding angles still would have the same measure. So these are the two things that must be true. And you can write this right in that box right there. You guys just told them to me. Now we put them in our notes. When I say corresponding angles, I'm just talking about angles that match up with each other. They line up. Some more symbols here. That's the angle symbol. So I'm saying angle X. Rather than writing out the word angle, just say angle X. Which angle does angle X correspond to? Which angle in the other triangle does angle X correspond or match up with? Cameron? Angle A. Are X and A congruent, Cameron? Yeah. They're both 90, right? They have the box in them. So we're going to say angle X, I don't know if you knew the symbol for congruent, an equal sign with one of those tildes, is that what you called it? An enye? So angle X is congruent with angle A. I'm going to find another pair of corresponding angles. I'll say angle Y. And going back to a rule, you told us this angle Y corresponds with which one? Or is congruent? Angle Z is congruent then with the only one left, angle C. And the arc numbers will tell you that. Angle C and angle Z both have the two arcs, which imply that they're congruent. Angle Y and B both have the single arc, which implies congruence. Obviously, the box means right angle. 90 degrees is always congruent to 90 degrees. So corresponding angles are congruent. We've proven that already. So that's step one. Step two would be to prove the corresponding sides are proportional. I'm not going to do that yet because I don't even have side links here to do it. But here's what I want to show you. Which side would correspond to XY? We label sides by the two endpoint vertices, by the way. So I wouldn't call this side X or side Y. I'd call it side XY. Ava. AB. So what we would have to show here, guys, and you can write this, we would have to show that whatever XY is, the length of XY, compared to its corresponding length AB, would be in proportion with another pair of corresponding sides. Okay? So XZ, I think you would agree, AC would be corresponding. So once I found these side lengths, if that's a true statement, if those two ratios are proportional to one another, then we're in good shape. We still have to prove the third. You can't just prove two because it's possible that the third side makes everything disproportionate. So then we would just write, just to finish this off, this would also have to be equivalent to YZ to BC. BC, CB, doesn't matter the order that you put your endpoints, okay? It really doesn't to me, okay? But both of these things being true would prove that these are similar, okay? And I want to do that right now. I want to look at an example that actually has numbers on it so that we can see that. So you guys are going to look at, it's at the top of the next page. It's the two trapezoids that you, unfortunately, do not have labels on yet. So I'll give you a minute. Just copy down what I have here onto your blank trapezoids. And I'm going to add some arcs here for us. So one thing you do not have to do when you're proving similarity, for me at least, I don't need you to write out like the angles being congruent every single time, like we did on that first example. This is one of those ones where you can kind of look and tell. For instance, If I ask you which angle correspond with angle A, you would tell me it is what angle? Which angle on the second trap corresponds? Max. N. Was anyone thinking N like Max? Was anyone thinking differently? Brooke? It could be either N or O, depending on how you rotate or whether you reflect it, meaning like flip it up. If you just flip it up like this, O and A would correspond. If you rotate it, then N and A. It doesn't matter, okay? So then A would correspond with, since Max gave us first N, that would make O and B, or B to O. M, since it gets rotated, lines up with D, and then C would line up with L. And it doesn't matter because you notice with these arcs, single arcs line up with single arcs, doubles with doubles, so the corresponding angles are congruent. Proven. All right, let's look at the ratios of the sides now, okay? So a pair of corresponding sides, just to use the highlighter one more time, AB corresponds with ON, right, or NO. So if I write the lengths of those as a ratio, I would say 9 centimeters to 6 centimeters. I'm going to find a different pair of corresponding sides, because if this is proportional, then these must represent equivalent ratios. Since I put the big triangle first, or the big trapezoid first, the 9 to 6, I've got to put the 12 to the 8. And then pause here and check to see, is that a true statement? Is the ratio of 9 to 6 equivalent to the ratio of 12 to 8? And yes or no, I need you to prove it to me, one way or another. Whether you're thinking yes, whether you're thinking no, need some proof, some verification. How many say, yeah, I think this is a true statement? How many say no? I don't think it is. I look like I got more yes than no. Definitely more yes than no. So how would you prove it? What are you going to do? Cameron?
Well, I was saying, like, we can divide them all by, we can, what was I thinking? Oh, yeah. Okay, so if you divide the 9 and 6 by 3, you get 3 and 2.
Mm-hmm.
If you divide both of the 12 and 8 by 4, you only get 3.
So they both reduce down to a 3 to 2 ratio, which means it's equivalent. That's one way, certainly. Good. Kate?
Another thing, if I did is if I divided 9 centimeters across by 8 centimeters, and I got 72, and 6 centimeters by 12 centimeters is also 72.
Good. She used the cross multiplication technique and saw cross products. If cross products are equal, then you have equivalent ratios. That's good. Jack? Good. Scale factor. All right. The larger one is 1.5 times the size of the big one. At least that's what it looks like now. Okay. Did anybody divide like 12 by 9? If you did, 12 divided by 9 would be 1 1/3. 8 divided by 6, is that also equal to 1 1/3? Yeah? Okay. Lots of ways to prove it. 6 or 9 divided by 12, it's 0.75. 6 divided by 8, 0.75. Right? So all of those ways work. I only need you to find one way that works. But we're still not done. We've proven that, yeah, these pair of corresponding sides are proportional. I still have more to prove. Now, since this is an isosceles trapezoid, meaning these legs are equivalent, I really only have to take one more pair of corresponding sides and match them up. Okay? So I would do a 6 to 4 ratio. Does 6 to 4, is it equivalent with, you'd really only need to test it with one of the other two, because we've already proven that those two are equal, so as long as this fits in with something else. Is that true? Some of you are shaking your head. Yeah, it is. Absolutely. Whichever way you decide to prove it, that is true. So that means that these two trapezoids are similar. So we're going to use our newfound symbol here. Not newfound, it's just maybe redefined symbol. So I'm going to take this and say trapezoid ABCD. There's no fancy notation for trapezoid. You just list the vertices. ABCD is similar, but here's the key. I can't just randomly put the vertices of the other four any way I want. You have to put it in the order in which you've labeled the first one. For instance, I have put A first, so then I need the angle that corresponds with A to go first, and then B, and then C. We have some flexibility here because, like we said, we have the way we orient it can change. But the way Max said, he put N first with A, so I'm going to put N first here. B, that would be O. And then, so since we rotated A, B, C, that would be L. I always hold my breath when I do this and hope it doesn't spell anything inappropriate, right? I don't think Nulm means anything, so I think we're safe, right? But that you might not like notice or think that it doesn't really matter like the way you label it, but it certainly does. So if I would have put, for instance, if I would have put B, C, D, A, if I would have chose to write the vertices in that order, which I'm perfectly fine in doing, then tell me how I would have to write my second one. Nadia? Yes. Isn't that like a yoga thing? Isn't that what people say? Like, are people that are meditating? Is it Om or something? Whatever. We're touching all the bases today. Okay. So now let's go to the rectangles. Again, you have two plane rectangles. All you have to do is put the side links. Tell me why I didn't even put vertices on here. Like, I didn't label. Any idea why? And yeah, they're all 90-degree angles anyway. It's not important. For identification purposes, yeah, you could say yeah. But all I ask are they similar? Okay? So it doesn't matter how you twist them or turn them or flip them or whatever. They're all 90 degrees. You need to pay attention to the side links and find your corresponding side links and see if those work. So do your test for me. What do you think? Which, it's a yes or no, but invariably it's going to be followed by prove it to me. How many have an answer? Yes or no? Marion, what do you think? She matched up corresponding. She put the long side of the one compared to the long side of the other, short to short, which is a good way to do it. And she's saying this is not equivalent. And her way is to divide 14 by 18 and 4 by 4.5. Some of you might have cross-multiplied, figured that out. Maybe you divided 18 by 4.5. Either way, I agree with Marion. This is not equivalent. So therefore, they're not similar figures. So that proves that not all rectangles have to be similar to one another. Some people think that originally, that all of them have to be similar. Okay. So that's proving whether or not they're similar. Now I'm going to tell you that they are similar. This next one, these are similar triangles. You then have to find the missing sides to make these true. So here's the deal. I'm going to say triangle XYZ, XYZ, and it works out is similar to triangle ABC. So there's the statement of similarity. You know that's true. I'm just going to turn you guys loose and you guys figure out which or what is the value of x and y and do it whichever way you want to try. All right, and then share with each other what you came up with. So a couple minutes to label first what I have up there and then find the missing values. So if you checked with someone else, can somebody tell me what you got for your value of x? Issa, what do you have? 17.5. Anybody else get 17 and a half for x here? Okay, good. I like 17 and a half for x. We'll come back to that. What do we get for y then? 17.5 meters. What about y? Ava? Anybody get 13.45? Yeah, we'll go with that. Good. Okay. So as you know, I'm going to want to know how we came up with this. So can somebody explain? We'll start with the x value. Can somebody explain how you came up with this missing value of x? Go ahead, Emily. Very good. She set up a proportion, which I would always recommend because we're good at these. She recognized that 10 corresponds with x, so she wrote one ratio of 10 to x. The other pair of corresponding sides would be 9 to 15.75. How many of you used a proportion like Emily? Okay? Give me a different way then that you could get 17 and a half. Because you don't have to do it that way. Go ahead, Issa. So go back to what was the first thing you said? You did x, y, and AB. You divided them. Yeah, she found out that the scale factor here is that the big one is 1.75 times. She just found a pair of corresponding parts. How many of you figured that out, that the big one was 1.75 times the size of the small? Okay, and then if you do that, 10 times 1.75. Good. All right, anybody have a different way of getting? Go ahead, Jack. That's fine. Yes, just a decimal.
And I did that times 23.54, and I got 13 point. Oh, that's for Y.
For y, yeah. Mm-hmm. Yeah, good. So he figured out that the small one is, what was it, about 0.5? Okay. Yeah. I like all of them, all right? All of those ways work for me. If we were going to do a proportion for y, you could do something like, I would always keep the same original, 9 to 15.75, but then it's a y to 23.54, and then just solve that out, and you're going to get that 13, about 13 and a half almost. Okay, great. All right, let's go. Let's see if we can get this last one in here. This one's a pretty quick one. We have two trapezoids here. Again, the vertices aren't labeled, but look at how you could rotate them and find corresponding parts. Okay, we're telling you that they're similar, so you don't have to worry about proving that. You just have to find what n is here. So maybe you find a scale factor. Maybe you set up a proportion. If it would help you, you could certainly label the vertices. These were certainly not drawn to scale, by the way. If you're looking at them and thinking, wait, this doesn't look like it's drawn accurately, that's because it's not. Before we go, anybody have that value of n? What is it, Jack? 56. The scale factor is 8. The bigger one is 8 times the size of it. Multiply 7 by 8. Very good. All right, guys, I'll see you tomorrow.